So we come to the last point before the Bode plot is appearing, amplitude and phase curve. Here very simple, we have the following situation. Again, in this case we set sigma to 0. So our f of p is converted into f of omega, the complex frequency response. The complex frequency response is a complex function, has a magnitude and a phase. And what we do with amplitude and phase curve is very simple. We display the magnitude value versus omega, and we display the phase curve versus omega. So we get two curves. In our example here, as the demo, we have this curve. Yeah, 0 means here we have omega 0, DC case, and we have f0, that means no gain. That is the demo f example. The phase, I don't know, because at this time the phase is not so interesting for our situation. Let's wait for the next point. This is possible that we display amplitude and phase curve in that way, but not common. Common is the same information now should be displayed in a diagram where we have not linear axis but logarithmic axis, and then this is called the Bode plot of my system function. So this is chapter 3.6, the Bode plot, and I want to spend a little bit more time on the Bode plot because this is the most important display of a system function in this lecture, because in chapter 5 you will see there is a very famous, helpful and easy to use method to design controllers if you have the Bode plot of your process. Yeah? The Bode plot is a very important point. So you have to work with Bode plots, understand all about Bode plots, and I think I will use this very extensively in this lecture. What is a Bode plot? A Bode plot is similar to amplitude and phase curve in linear case, but with partly logarithmic axis. First, we want to display not f magnitude, but display the logarithmic value of the magnitude. And it is common that this will be expressed in dB values. So the value, the logarithmic value of f, then is multiplied with 20 dB, and then we have a dB axis. To draw here some values which should be known, or you can learn it by heart. This is f magnitude and this is 20 dB, the logarithmic value of magnitude. This only works if f has no physical unit, that's clear. It's a ratio of input-output, so it could be a ratio of voltages. For example, if we have unity gain, input amplitude is equal output amplitude, then this is 0 dB. I have forgotten to mention that, what happens if we set sigma to 0? What type of signals do we have here in this display? We have to note this only valid. This information is only usable, valid for sinusoidal signals. For sinusoidal signals. So an amplitude and phase curve or a Bode plot contains information about sinusoidal signals and nothing else. No switched signals, no steps, no impulses, no information about this, only information about sinusoidal signals. Some other values. So what happens if we have a gain of 10? If the amplitude, if the output is 10 times larger than the input amplitude, then the logarithmic to the base, this is a logarithmic value to the base 10. Yeah, then the logarithmic value is 1 times 20 dB is 20 dB. Yeah, these are all dB values. I should note this, otherwise it could be dangerous. The same is with 100. If I have a gain of 100, we have 40 dB. Or if we have 0.1, we have a negative 20 dB. So a negative value in the dB value means damping. Yeah, then the output amplitude is smaller than this, and we have a stop band. Yeah, the same is with we have 1% output of input, and this is negative 40 dB. Some other values is this factor of 2 is well known as the 6 dB value. Yeah, 6 dB means factor of 2, roundabout. It's not exactly the exact. These values are exact calculations. This is only approximate factor of 2. If we have square root of 2, we have 3 dB. Or if we have 1 divided by square root of 2, then we have negative 3 dB, still known as the indicator for a band border, where the pass band goes over into the stop band. Also, this is a minus 3 dB value. Then a very important value is 0. If we have no gain, if there is a broken cable, what happens with my dB value? The dB value is the logarithmic factor of 0 is negative infinity. So the broken cable is a value we cannot draw on a Bode plot curve. And finally, maybe you should know what is 1 dB. 1 dB is a factor of 1.12. So if 0 dB is 1 and 1 dB is 1.12, this is 12% larger than this. So you see 1 dB, that's 1 millimeter in the normal scaling of a Bode plot, is in reality, in linear scale, is a 12% change. 1 dB seems to be very small, 12% is rather large. So if you want to hide large changes here, just draw it as a dB curve. Then you can hide and make your presentations in a good way if you want to display large changes with small curves, curve changes. Okay, these are some points. The question is now, what is a display? How can we draw a Bode plot? We have a vertical axis. F will be displayed in dB, and the omega value also will be displayed in a logarithmic case, log omega. That means we have here, for example, if this is 1 and this is 10, then this will be 100. Now that is the logarithmic scaling of omega, and the dB scale because the dB value is already logarithmic, is linear. If this is 20, then this is 40, and then this is 60, expressed in dB. So this is the scaling of the F curve. This contains all information about the magnitude of omega, and the phase curve, normally we have negative phase, is also displayed in logarithmic axis, but the phase is displayed linearly on the vertical axis. Here again we have the logarithmic scaling of omega. Omega 1, 10, 100 is displayed in that way. And if I display those curves in that way, then we call those together the Bode plot. The Bode plot contains two curves. Yeah? This is the Bode plot. The question is, why displaying in this logarithmic axis? What is the advantage and the disadvantage? You should know something about advantages and disadvantages. I think that should be the next point. Why logarithmic scaling? First, the advantage of logarithmic axis of the omega axis. Advantage of log omega axis. If we compare linear with logarithmic scaling, let's do this here in the next picture. If this is omega and this is log omega, say this is 1 and say this is 100, then of course these both points could be identical, same distance. Where is 10? If this is 1 and this is 100, in logarithmic, in linear scaling, we can say, okay, where is 10? We can say this is 0, and 10 is then 1/10 of this distance, so this is 10. So you see the range between 1 and 10 is 1/10 of the range 10 to 100, but normally we want to have low frequency and high frequency range with the same resolution, with the same on the same range. So 1 to 10 and 10 to 100 displays much more better reality as the linear axis. Yeah. Problem is disadvantage. We can say advantage is better display of low frequencies, low freq behavior. Yeah? Low frequency behavior. A disadvantage, where is the 0? Where is the DC case? We have to go on here. This is 0.01. This is 0.01. You see the DC case, omega 0 is not on the axis. So we can say the DC case, which is also important and famous, is not available in the Bode plot. In the linear case, it is just this point. In the logarithmic axis, this is in the negative infinity distance, so not on the paper. That is a disadvantage of the logarithmic omega axis. Advantage, low frequency ranges can be better analyzed with the logarithmic axis. Okay, that is the advantage, disadvantage of the logarithmic horizontal omega axis. What is with the dB value? Why dB values? Advantage of dB values. T1 advantage of dB values. If I have one filter, F1, and I have a second filter, F2, and I want to know the total behavior of a series connection, then we have learned in chapter 2 the total system function of a series connection is a product of the transfer functions. Okay. If we have the Bode plot, what happens with the Bode plot of series connection? In the Bode plot, we know that we have to display the logarithmic value of f1 magnitude times f2 magnitude, and the advantage of logarithmic scaling is that the logarithmic value of a product of two numbers is just the sum of the dB value of filter number 1 plus the dB value of filter number 2. You can add curves. Yeah, if you have a series connection of filters, and that is true in closed loop systems, because then we have a controller and series connection with a process, then we can just add the curve of the process plus the curve of the controller, that we have the curve of the open loop system. So this is a very big advantage of the logarithmic vertical values, dB values. The last question is why we not display phi in logarithmic case. Answer, very simple. Phi in linear scaling, because if we have because phi is exponent, yeah, f, the complex function is f magnitude times e to the power of j phi. That means f1, f2 is the product here of two functions is f1 magnitude times f2 magnitude times e to the power of j phi 1 times e to the power of j phi 2. And if you multiply two exponential functions, you know you have to add the phase curves. You have to add the phase values, and that means the series connection of two filters is the multiplication of the magnitudes, the addition of the dB values, and just the addition of the phase values. So it's not necessary to display the phase curve in a vertical logarithmic scaling, because the two phase curves are added in a series connection. And finally, the last advantage of the double logarithmic display is if we have our filter functions, then we have polynomial functions in the numerator and denominator, and the double logarithmic display gives straight line asymptotical curves. The asymptotical curves will be explained and used later if we go more in detail in linear block structures. Yeah, so wait for chapter 3.7 where we go into many standard block systems that we will use the asymptotical display method of magnitude curves in more detail. Jetzt the last point I want to mention in Bode plot curves is how to measure Bode plot values. How to measure a Bode plot. First, we should know that a Bode plot is a display of the it's the amplitude and phase curves, the display of the frequency response. We ignore sigma, so we just work now with the frequency response, and the frequency response deals with sinusoidal signals. You can measure this with sinusoidal generator, sinus generator, plus scope. Better, of course, in the lab we will use a gain phase analyzer, or gain phase analyzer. But with a sinus generator this is possible. So simple devices. Let's assume that this is my device under test, my filter I want to measure. We assume that this is grounded. There's a ground line. Here we have the input signal U1 of t. Here we have the input signal U2 of t. And now we connect a sinusoidal generator. So that U1 of t is just an amplitude A, and this signal has a mathematical sinus function, and we have a frequency omega t. And omega, the frequency, is changed. So if we measure with one frequency and one amplitude, we have one signal at the input, and then in a linear filter we know something about the output signal. We know that U2 of t, in a linear case, if U1 is sinusoidal, then we know that the output is also a sinusoidal signal. Not limited, not without saturation and so on, just sinusoidal. We know furthermore that the frequency of the output signal is the same than the input signal, with one difference: there could be a phase shift. This is exactly my phi of my frequency response. And the output amplitude also depends on my filter function, is different, but the signal form is the same, the frequency is the same, and there's a phase shift, and the connection to our system transfer function is very simple. The magnitude is nothing else than the ratio of the output amplitude divided by the input amplitude. So this is the connection. The phase shift of two sinusoidal signals are the phi values in the phase curve, and the magnitude curve contains points, and each point is the ratio of output divided by input amplitude of the sinusoidal signal at this frequency. So omega is a parameter. If you change omega, then measure B, divide by A, and then you have that point of magnitude. So measure the phase shift between both signals at this frequency, and then this is the point of the phase curve of the Bode plot. That's a way to get information or measurement of Bode plot values.